Okay, so we're going to do reaction diffusion equations now. Make sure I can spell diffusion. Alright, so the chemical modelling of chemical reactions with diffusion, which means the particles can move. So it's quite a beautiful area. It's quite a beautiful topic. It's one of my favourite part of the course. It's not as tricky as the KDB, and we can tackle it and attack the problem numerically, find travelling wave solutions, and all this stuff. So let's get started. So first of all, we've got a bit of chemistry here. So we start with simple decay. So we're not writing down chemical equations here. So we're kind of just writing down some mathematics that models it. So it's maybe not quite like it might upset the chemists. But we let P be concentration of chemical P. Of P, big P, and A, little a, is the concentration of big A. So our equation is really simple. It's dP dt is equal to minus Kp. So it's just like a radioactive decay. So spontaneously P turns into A at the rate dependent on the number of P. So this is sort of a fair model for, you know, the breakdown of ozone in the atmosphere or something like that. That's what happens. It just spontaneously breaks down. Okay, maybe better be careful, but some no expert on ozone breaking down is making that up, but some sort of chemical like that. And dA dt is equal to Kp. Okay, so we can solve these pretty simply. And we get P is P naught e to the minus Kt, and A is equal to A naught plus P naught 1 minus e to the minus Kt. And the second one here you just find by integration, right? This is just the integral of K times that. And then you get some boundary condition of A naught. Okay, no problem, that's simple decay. So what we're interested in here is this quadratic autocatalyst. So this is a classic reaction. It might not know how common these are, but they produce beautiful patterns and they're kind of well studied. But basically we have A plus B goes to 2B. So basically what happens is A is decaying to B, but the presence of B speeds up the reaction. So if A is sitting there by itself, it never will turn into B. But if an A hits a B, right, like you've got a little A here floating around and hits a B, when they collide, then they turn into 2B. So this, it's an autocatalyst. So as soon as the B concentration starts to rise, it'll make more A, and then you get a runaway sort of reaction, converting all of the A to B. So the equation is, as before, you know, little a is the concentration of the species A, and B is the concentration of B. The dA dt is minus KAB, and dB dt is equal to KAB. So the idea of the model is really simple. It's just that if you know, the rate's proportional to the amount of A and the amount of B, okay, and then A is turning into B. So we can solve these equations. Oh, whoops, don't do that. We can solve this equation by observing that dA plus B, okay, which is kind of obvious, it's conserved, right, because there is equal to minus KAB plus KAB, so this is 0. So A plus B is a constant. So we can go A plus B is equal to whatever we started with. So we know once, so if we can substitute that, and then we end up with dA dt is equal to minus K, might as well follow the note, so that's alright. So it's dB dt is equal to minus KAB, sorry, plus KAB, and then A is equal to B minus that. So it's K times A, which is A naught, plus B naught minus B multiplied by B. So this is like a, this is completely the same as the logistic equation. You can write down a solution of that. Okay, dot, dot, dot. Solve using separation of variables. And it's one of the your problems in the assignment. Okay, so I'm not going to work it out. Okay, the note solution's given here. Okay, so that's no problem. You know, this is just a, you know, you can do this by separating it, taking it out here, and it's like if you look at it on a phase line, you've got an equilibrium points when B is 0 and when B is this starting point. Okay, the amount that you started out at the end. Okay, so yeah, here's the phase line. Here's the two equilibrium points. When B is equal to 0, then dB dt is 0. Okay, and over here is when B is equal to A naught plus B naught. Okay, everything has become B. Okay, and then up here is a bit silly because one of these chemical species become negative, but the equation flows like that into this equilibrium point. All right.